Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So in this module we are trying to study how the operating system manages the CPU by providing an abstraction of a process, right? So within this module we are currently on the first topic, that is process introduction. So here in this topic, through a series of videos we are trying to understand what is a process and how does the operating system implement this abstraction of a process over the CPU, right? So we now have a fair idea of what is a process, right? In the previous few videos we have talked about it in great detail. So there is another concept that is called the state of a process. So a process can be in different states during its lifetime, and we want to study what are all these states. Once we have a good idea of what are the different states that a process can be in and what exactly these states are, we have a fair picture of the life cycle of a process. That is, what are all the different activities that a process does during its lifetime. So in this video, at a high level, we want to understand the life of a process. So without further ado, let's get started. So if I ask you the question that can you describe the events that could occur in the life of a process, then what are the events that come into your mind? Two events are very certain. The first is that obviously the process will be created. So as you can see in this slide, I have listed some events. So the first thing that happens and is bound to happen is that the process will be created. And if a process is created, then it is also certain that at some point in time, it will be destroyed. So creation and termination are two events that are certain to happen in the life of a process, and these two are important events, right? And what happens between creation and termination? Obviously, it will do some useful work. So the process has been created in order to execute instructions. Basically, a process is a running program, and what happens when a program is running? Its instructions are being executed by the CPU. So the most important part in the life of a process will be the execution part. So a process is created, then when it is running, the instructions that are there as part of the program, they are getting executed. And once the instructions, all of the instructions are executed, the program finishes and the process can then terminate, right? So these three are the at least these are the basic events that we are sure that will happen in any in the life of any process. It will be created, it will definitely be destroyed, and between creation and destruction there will be this execution of instructions. So now the question is, are there any other events that happen during the life of a process? So it is not the case that for all the period of time the process is executing instructions. If we recall the concept of time sharing, right? How the operating system manages the CPU. First of all, there are limited number of CPUs in the system, and the number of processes in the system is way more than the number of CPUs that are available. So this is a basic constraint, that the number of CPUs is limited and very less as compared to the number of processes. And now we also know that the operating system handles this situation by time sharing the CPU between all the different processes. So the control of the CPU is given to the different processes for brief periods of time, and frequently the control of the CPU is switched from one process to another. So you can see clearly that a given process will not have the control of the CPU for its entire duration, right? So at some point in time, when it is executing instructions, the operating system will decide to take the control away from the process. So as you can see, there are certain other events also that happen during the life of a process apart from execution of instructions, because it cannot execute forever. The CPU will be taken away from the process in between, right? So let's understand this situation with an example. So here we have a hypothetical example. As you can see, there is a computer system with one CPU, and there are n different processes that want to run on the CPU. So basically, we are trying to understand what else happens during the life of a process apart from creation, termination, and execution of instructions. Definitely, there are certain other events or activities that happen during the life of a process. So to understand this, recall that we have a limited number of CPUs in the computer system. As you can see, the number of processes generally that we have in a computer is way more than the number of CPUs, right? So as an example, here you can see there is one single CPU and there are n processes that want to run on the CPU. Now, we already know how the operating system tackles this situation. It handles the situation by the concept of time sharing. In time sharing, basically the CPU time is shared among all the different processes in the system, right? So the way this works is that each of the process gets to execute on the CPU for a brief period of time, and after it has executed some instructions, what the operating system does is that it takes away the control of the CPU from that process and then gives it to some other process. And in this way, it frequently switches the control of the CPU between different processes so that all the processes can execute their instructions. So even if we have like few CPUs in the system as compared to the number of processes, still by sharing the CPU, the operating system enables all of the different processes to run on the CPU. Now, as you can see, when there are limited number of CPUs, there will be some processes that will be executing, and the rest of them will have to wait, right? These processes will be waiting for the control of the CPU. So, for example, in this case, there is a single CPU. Let's say the operating system decides to allow P1, process P1 to run on the CPU. So, as you can see, only P1 is running. It is executing instructions. The rest of the processes, right? There are n processes in the system in total. One is executing its instructions. The rest n minus one process has to wait. So as you can see, waiting for the CPU to be assigned is a very important and major part during the life of a process, right? For most of the time, the process will be actually waiting for the CPU to be assigned to it, right? So for example, let's say now process P1, the control of the CPU is taken away from process P1 and assigned to some other process. Let's say Pn minus one. So now you can see process P1, which was executing its instruction just a while ago. Now it has to wait again for the control of the CPU, right? And now process Pn minus one, which was waiting for the control of the CPU just a while ago, is executing instructions. So now we understand that apart from creation, termination, and execution of instructions, waiting for the CPU to be assigned is another major part of the life of a process. So that is why we are going to modify this diagram. Basically, we are trying to construct a diagram which will be a depiction of the life of a process. In that diagram, there will be different states, you can say, in which the process is during different times of its lifetime. So as of now, we have three different states. The first is the creation. Second is the state where the process is executing instructions. And the third is when the process has terminated. So all of these are activities that the process undertakes during its lifetime. So now we understand that apart from this, there is another important activity during the life of a process, that is waiting for the CPU to be assigned. So let us understand the diagram. So there are four different major activities that can happen during the life of a process. As of now, we are going to modify this diagram again. So creation is there. Then once the process is created, then it might be the case that it is not assigned the CPU just after creation. It has to wait for some time. So a major part of the life of a process is waiting for the CPU. Then once the CPU is assigned to the process, this event is known as being scheduled, right? As you can see, when a process is allowed to run on the CPU, we can say the process has been scheduled to run on the CPU, right? And when the process is running on the CPU, it is executing instructions. Now, when it is executing instructions, there are two possibilities. Either all of its instructions get finished and it can terminate. So termination of the process can happen, or it might be the case there are several instructions and it will take certain significant amount of time for the process to execute, right? So in that case, as we know, the operating system will not allow the process to execute forever. At some point, the operating system will take away the control of the CPU from the process. So it will stop executing instructions. And that event we can say is that the process has been descheduled from the CPU, right? When the process is allowed to run on the CPU, we say that the process is scheduled. And when the reverse happens, when the control of the CPU is taken away from the process can no longer run, we can say the process has been descheduled from the CPU. And in that case, it goes on to waiting. So here the process is although ready to run, right? It's just not able to run because the number of CPUs in the system is not enough. So here the process will wait for some time till the CPU is assigned again to this process. And you can see between these two states, it will keep on switching between these two states. Eventually, it will have its last execution burst and it will terminate. So these are the four different states we can say as of now that are there in the life of a process. These are the four major events we can say or activities that a process undergoes during its lifetime. So now let us understand what are the other states that are possible during the life cycle of a process. So to understand this, let us come back to our hypothetical computer system where we have a single CPU and different processes that want to run on the CPU. So let's assume that process P2 or the word processor is scheduled to run on the CPU. It is executing instructions and then it initiates an IO operation. It could be an input operation or an output operation, and it has to wait for that operation to complete. So let us talk a bit about input and output operations because they play a very important role during the life of a process. So most of the applications would be doing in input and output operations, right? So basically what happens is that the IO devices are very slow compared to the speed of a processor, right? If you talk about the CPU or the processor, it can execute millions and billions of instructions per second, right? Its speed is very fast. But if you compare this with an IO device, IO devices operate at the speed of the human user. So let's take the example of the keyboard. So we are typing characters. So what is our speed when we type characters, right? It would be few characters per second at best, right? And similarly, let's take the example of mouse. Very infrequently, we give the like mouse inputs, right? So these are inputs that arrive at a very slow rate, right? So the point is that for IO operations to complete, it takes considerable amount of time as compared to the time it takes to execute instructions, right? So during the time the process or the application is waiting for the input or the output operation to complete, during that time it cannot execute instructions, right? Basically, let's say the word processor, let's say it's waiting for some input to arrive. It has initiated an input operation, then it will take some time for that input to arrive, and unless that input data is there, it cannot do the processing. So the processing is blocked upon the input data to arrive, and that data will take some time to arrive, right? So during that part it cannot execute instructions. The point is this. So during an IO operation, the process is blocked and it cannot execute instructions, right? And this waiting period, this blocking period can be long if we compare this to the speed of the processor. So as you can see in this example, process P2 has initiated an IO operation and it cannot execute instructions. So what the operating system does is that it takes away the control of the CPU from this process. Why? Because anyway it is not able to execute instructions. The processing cannot continue until the further data is there in case of input, or let's say if it's an output operation, once the output has completed, only then further execution can proceed. So the situation is that let's say a process has initiated an input or output operation. This operation will take some time to complete, and during that time the process cannot execute. So it's best that the operating system give the control of the CPU to some other process which is kind of ready to execute. So now there are two kinds of waiting here. So as you can see, process P2 is also waiting, and process P1 to Pn, all of these are also waiting, but there is a difference. Process P2 is waiting in the sense it cannot execute instructions even if you give it the CPU, unless the IO operation completes, unless the data arrives or whatever the operation was there, unless it completes, it cannot execute instructions. It's in a blocked state, right? Here in these processes, the waiting is of a different nature. All of these processes are ready to execute. It's just that they do not have the control of the CPU. And once they get the control of the CPU, then they can execute their instructions. So what the operating system does is that when a process goes into a blocked state, it is blocked for some event to occur, right? It could be due to an IO operation, or it could be due to some other operations also. In those cases, the operating system takes the control of the CPU from that block process and gives it to some other process which is ready to run. So as you can see in this case, let's say process P3 is scheduled to run on the CPU. And after some time, let's assume that the IO operation has completed. Now the word processor is ready to execute, right? The IO operation is completed. Now it can do the further processing. So after some time, the operating system, let's say, deschedules P3, takes the control of the CPU from process P3, and then again it can allow process P2 to run. It can now start executing instructions, right? So you see how the operating system is scheduling the CPU between different processes, and how there are two different types of waiting involved. So this diagram, let us modify this and include that another waiting state. So now we have another state. This is where the process is waiting for an event to complete, and this event could be anything like an input or an output operation to complete. There are other reasons also why a process might wait. So in the next module, when we study about process synchronization, we will see there are certain events for which that are due to synchronization purposes, that one process has to wait for another. So the point is, there are certain events due to which a process is blocked. It cannot do further processing, right? And during this state, what the operating system does is that it takes the control of the CPU from that particular process and puts it into a block state. So as you can see here, the process was executing instructions, and when a situation arises that it has to wait for an event, and without that event being completed, it cannot do further processing. It has been put into a kind of block state, and it will wait for that event to complete. Only when that event is complete, then it is ready to execute instructions. So and when it is ready to execute instructions, then it can be scheduled. So there is a difference between these two kinds of waiting, as I already said. In this case here, the process is ready to execute instructions. It's just that it is waiting for the CPU. Here the waiting is of a different kind. It is kind of a block state. Here, unless that event occurs, even if you give the CPU to this process, it won't be executing instructions. And once that event completes, then it can be put into this state where it is waiting for the CPU. So this is how the different states look like during the life of a process. And what we do in the context of operating system is that we give all of these states a particular name. So for example, you can see each of these states has been given a name. Let's understand these names. So whenever a process is created, that process is given the new state. It is said to be in a new state, right? Then from new state, it transitions into a ready state when it is basically ready to execute instructions. Here it is just waiting for the CPU to be assigned to it. Then after ready, let's say the CPU is assigned to it, we say that the process which is in ready state, out of all the ready processes, there will be multiple processes in ready state. The CPU will pick one of them and schedule them to run on the CPU. When it is actually executing instructions, that is when it is set to be in running state. And finally, from running state, it could either be terminated, right? Let's say it finishes its instructions, then it can go to the terminated state. Then or otherwise, this control of the CPU can be taken away from that process which is running, and then it can go to ready state. In this case, the control has been taken away just because it has executed for enough amount of time, right? Or this process which was executing instructions, which was in running state, it could go into a block state. Basically, it is now waiting for a particular event to occur, and unless that event occurs, it is in a block state. It cannot do further processing. So it can transition from running to waiting state, and only when that particular event for which the process was blocked or waiting for occurs, only when that event is completed, then it can then it can transition into ready state, and then the operating system might allocate the CPU to that process at some later point in time. So going from running to ready and ready to running is easier. Here the process is actually ready to execute instructions. But if a process goes into the waiting state, it cannot go directly into the running state, because even if we assign the CPU to that process, then it cannot execute instructions. It cannot do processing unless that event occurs. So if a process goes into waiting state, then it will first go into ready state after that particular event occurs, and then it can be scheduled to run on the CPU. So these are all the different states that a process can be in during its lifetime. And this diagram is called the process state diagram. These ovals that you see, these are the states, and these arrows are the transitions between the different states, right? So this diagram, basically this process state diagram, gives you a brief overview, a rough overview of what are the different events that happens during the life of a process. What are the things that a process does during its lifetime? A very important point about this process state diagram is the number of processes that can be in each of these states. So as you can see here, it's written that the number of processes that are in the running state depends on the number of CPU, while many processes can be ready or waiting. So what I mean is that so the number of processes that are in the running state is at max the number of CPUs. So if you see, if in any computer system, right, when a process is in running state, it is executing instructions on the CPU, right? So the number of processes that can be running is at most the number of CPUs that are there in the system. It can be less than that, it can be equal to it, but cannot be more than the number of CPUs, because CPU is where the process will be executing instructions, right? So if a computer system has 8 CPUs, then there can be at max 8 processes that can be in the running state at any given point in time, right? In the hypothetical example also we saw earlier, there was one single CPU, and at any given point in time there can be only one process, at max one process that can be in the running state. So this was about the number of processes that can be in the running state. If you talk about the ready or waiting state, then this is not limited to any particular number, right? This is kind of unrestricted. So the number of processes that can be in the ready state or waiting state, it could be any number. It could be less than the number of CPUs or more than the number of CPUs. It is kind of unrestricted. So this was about the number of processes that can be in these states. So another point is that this process state diagram that we just studied, it's not only important for us to get an idea of the life of a process, it is also very crucial from the perspective of the operating system. Because if you see, it's the operating system which has to implement this time sharing. It has to share the CPU among all these processes. And in order to properly share the CPU among these processes, it must have a clear idea of which state the processes are in, right? So there will be certain processes which are in ready state, some processes would be in waiting or block state, and the operating system must clearly know which process is in which state, right? Because when it comes to making a scheduling decision, if the operating system assigns the CPU to a process which is in a waiting or block state, then that would be a poor scheduling decision, because even if you assign the CPU that to that waiting process, it is blocked or waiting for a particular event to occur, and unless that event occurs, it cannot do processing or execute instructions, even if you assign the CPU to that particular process. So this will lead to poor resource utilization. The CPU is assigned to a process which is kind of blocked, right? So instead the CPU should have been assigned to a process which is in the ready state. So the processes that are in the ready state, they are ready to execute instructions, right? So you can see while making these scheduling decisions, that is to which process the CPU should be assigned, the operating system should have a clear idea of all the processes and which state they belong to, right? So finally, I wanted to show you a real example of how this process state is used. So here again, I have the process control block from the XB6 operating system. I talked about this XB6 operating system in the previous video also, where we talked about process control block. So XB6 is a toy operating system, you can say, mini operating system that has been designed at the MIT University for teaching purposes, right? So as you can see, this is the process control block from the XB6 operating system. It's based on Unix based OS. So here this field that you see, enum proc state. So this basically stores the state in which the process is. So for every process in the system, the operating system will have a process control block. And for each process in the process control block, there is a field called the process state, which can have multiple values, right? So as you can see, this is an enum, and these are the different states in which a process in x86 operating system can be in. So now a very important point is that the exact states that a process can be in, the name of, first of all, the number of states can be different in the different OS, and the name of the state can also be like different as per the OS. So as you can see in the XB6 OS, there's the waiting state has been named as sleeping. The running state has the running name only. The ready state has been named as runnable. So waiting state is sleeping, ready state is runnable, and running state has been named ready only. Also, there is the processes which terminate are assigned the zombie state. And so you can see basically the exact states are somewhat different in the x86 operating system. The one that we just studied had different states, but nonetheless the basic states would be the same. So the running, the ready, this waiting, right, all of these states will still be there. The names could be different, some other states could be also there, but these basic states would definitely be there in any operating system. The process state, these are the basic states, the ready, waiting, and running. Created and terminated are also basic states. So my point is, the number of states, the name of the states could vary as per the operating system, but the basic ideas remain the same. So guys, this was about the process state diagram. In this video, we talked about what are the different activities or events that happen during the life of a process, what are the different stages it goes through, right? So now I hope you have a clear understanding of what all happens during the life of a process, right? So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.